had a really awesome discussion this morning. They gave me a lot of pressure, so I just, at least a few questions, very general questions for the audience. And most of the time, the question is just, I think, more intended for junior researchers on, how to grow in the field of neuroimaging, in the field of data analysis. So my first question is, I summarize my question for Camille here, is that, in neuroimaging and data collection, we try to balance two goals. The first one, we try to get awesome data. We want to develop awesome hardware, right, to collect high quality data. The second goal is we want to collect vast amounts of data using more accessible equipment, 1.5 Tesla, 3 Tesla, everywhere in the hospital. Probably they're not great. Statistically, or from machine learning point of view, we want a lot of data to be able to train our awesome neural networks to make it work and so on. So these two aims can conflict, but maybe AI or machine learning can offer some exciting solutions. For example, you can collect a small amount of expensive high quality data and use that to enhance the data you have with lower quality, and et cetera, et cetera. So, that's the potential of AI. And my first question for our panelist, Camille, is that considering the advances discussed today in this section, the ultra-high magnetic fields, network-based approaches, where do you see the future of imaging techniques heading in the next decade? Should we collect as much data as possible, put them somewhere, and let machine learning AI to figure out what's going on, just like ImageNet, because of ImageNet we have ChatGPTs and so on, these generative foundational models, they're so cool. Or we should, invest more on high, sophisticated devices to collect better data. The data kind we have is not going to help us to answer the questions we want to answer clinically, or in clinical important questions. So that's the first question. Maybe we can start with Camille.
Yes, I think I was asked that question also, I think, at the end of my lecture, and I gave an answer, but I will try to answer again. I think that at least in the near future, we still will need to collect a lot of data in very advanced instruments. In fact, to be able to ask or answer the questions that you are posing. And I think that it's not quite clear to me if, let's say, the low quality data that you are, it's high quality data, but let's say that lower resolution, or in some ways sampling something at a lower rate, for example, not sampling Q space in the MRI, diffusion-weighted MRI as extensively, whether that kind of low-quality data still contains the information that we want. In other words, the assumption here is that if AI is going to help us, that the low-quality data has that information. We're just not able to extract it with our existing methods. And the AI then, by mapping from analyzing the low quality data and mapping from the high to low quality data, will somehow enable us to extract that information. It's a guess, but my gut feeling is that yes, I'm sure there's some additional information we are failing to extract from the existing so-called low quality data. But there's a limit to what we can obtain from such data, simply because it doesn't have a certain, the information content. For example, if we are looking at content about if the voxel has a lot of heterogeneity, and we are trying to answer questions about the sub-compartments of that voxel, there may be hints of that in that data, and I think I can think of examples of that for sure, and then AI type of methods, deep learning methods can extract that. But I think that there's a limit to it, and ultimately we will need also the very high quality data and to push the field forward.
Great, thank you.
Maybe I'll make it up. This morning we were talking about, several of us, about could we use our lower resolution DTI data. Lower being maybe we don't have multiple shells, or maybe we have lower p-values or something, and use the high, all the AI and all this other stuff to ultimately teach it how to get tractography. I think that would be hugely, incredibly helpful, because not everyone can collect HCP type data. Especially, like I consider myself like a cognitive neuroscientist that studies clinical questions, and a lot of times we have to scan our own people and our own participants, and we can't do all of the stuff that everyone does, and you're limited in time, you're limited in money, and so if we could have faster scans but use your AI to help us extract information out of it, it'd be great. And for better or worse, most graph theory stuff in the brain is parcellation based, right? So while I love the talk that Dr. Ubergo gave about like the DTI and you have the gyral bias, if you have a giant ROI that's 3 centimeters, the gyral bias doesn't matter anymore, because you have 70 patches of brain. You're not trying to see is it in that sulcus or on the edge of that gyrus, and I think that maybe the lower resolution data will work for that kind of thing.
I don't know if I can comment too much on this because neuroimaging is not my primary modality. The one thing that does come to mind that I sort of think about is there's maybe an analog in the neuropsychological literature where the level of granularity that you need oftentimes kind of is calibrated to the clinical question. There are things that you can get at if somebody already has like Alzheimer's, for example, in a very quick and efficient way that don't require a lot of resolution clinically. And the reason I mention it is because I think, to whatever extent this is sort of work for some of these questions, it seems like it's going to be less about the dimensionality or sort of sophistication within one modality and more sort of figuring out how to integrate across a few different systems at the same time. So like you mentioned cognitive reserve and behavioral data, in my sense is there's going to be some dovetailing or integration across a few different things, behavioral, background, medical risk factors, something like that, and imaging that will be very informative. So for what that's worth, that's something else just to kind of think about. I'll pass it on to somebody who knows more about it.
So I think it really depends on the application, right? So in ISMRM this year, there was a big discussion on low field MRI. So apparently the quality is not as good as your 70 or 10.5T, but really there's a lot of value with doing low field MRI, right? Things like stroke, you don't need high spatial resolution, for example. So it really depends on the application. So even for like segmentation, right? So what are you really trying to measure? Okay, so if you're interested in only like the overall white matter volume or the overall gray matter volume, I don't think a slight change in the resolution would matter that much. But if you're interested in the accumbens, which is a much smaller structure, then probably the higher resolution would give you some advantage. And I also think that we often separate the low resolution and high resolution. So in a low resolution image, we don't collect the higher k-space data, which gives the spatial detail. But is it possible to collect low resolution information and some higher resolution information, right? Then use deep learning to bridge the gap to do some data imputation to at least infer the redundant data. Like the multi-band example that Dr. Ubergo showed is a very good example on how to identify the redundancy in data collection. There's apparently a lot of redundant data that we've collected that that wasted scan time, right? So if you can identify those redundancy, and use interpolation or like the deep learning based interpolation techniques to help with recovering those redundant data, then you can speed up your acquisition and at the same time get the resolution that you want.
I guess the one thing that I would add, it would make me think of maybe one, at least kind of application specific, one kind of an untapped source is if you have rich kind of simulation models that you can generate synthetic data for. So in the field that I work in diffusion imaging, there's lots of rich biophysical models that allow you to kind of give particular kind of tissue parameterizations and then kind of acquisition parameterizations and simulate kind of high fidelity signals from that. And then you can imagine if you can only gather kind of low fidelity diffusion images, you could potentially offline use a deep learning approach to kind of learn mappings on synthetic data from low fidelity kind of acquisition design that you have to higher fidelity data, and then use this kind of inverse model to apply to kind of map to your low to high fidelity. Of course, the probably high fidelity isn't complete. Kind of all the information isn't contained in the lower fidelity, so there might need to be some kind of uncertainty quantification, some sort of probabilistic component to this, like a set of possible kind of mappings into the kind of higher quality or higher B value or what have it, kind of whatever acquisition parameters you want to adjust. But then I found it in work, especially for these kind of lower level image kind of reconstruction, inverse problem types of tasks. They're often for different applications exists kind of these folks who have really built these biophysical models that can be a rich source of synthetic data for you. Of course, the synthetic data isn't exactly what you see, so you have to worry about model discrepancy and these types of things. But yeah, that's my thoughts.
Great. Thank you so much for those awesome answers. So I'll move to, this is the most technical question I have in all my questions. I'll move to the next one. The next one, actually, I'm asking because we have a lot of junior researchers, PhD students also here. The questions are about balancing interdisciplinary skills. Neuroimaging research often requires expertise in multiple disciplines, including neuroscience, physics, electronic engineering, signal processing, statistics, computer science. It's very complicated, I have to say. I have to teach myself new stuff, every day, every month to be able to do something meaningful, interesting. So how did you manage to balance and integrate those different skill sets in your research? And what advice would you give to junior researchers trying to bridge these fields? Maybe we can start with Professor Yubil.
Yes, I mean that is a very important observation that in today's research, the kind of research we're talking about, trying to understand the human brain using MRI techniques or imaging techniques, etc., there are so many different disciplines involved. It's very difficult to master all of them. And essentially, I have tackled that problem by really collaborating people who are very good at various aspects of that. And I think that I talked about the Human Connectome project quite a bit in my lecture. That's in many ways a very good example of that. I mean, CMRR, my lab, is very good in hardware, and we have a lot of people, and we are very good at image reconstruction. But we don't put a lot of effort in, and we are not necessarily, we don't put a creative effort in, for example, analyzing the data that we ultimately get. And yet, in the Human Connectome project, we paired with Oxford, who actually put a lot of effort in to image analysis once they get the image in their hands, in terms of for a lot of image correction for motion, correction for this, correction for that, and then analysis using this method or that method. And it's also the same within my lab. I mean, when we talk about, I said, okay, we are good at engineering and image reconstruction. There are really two separate approaches there. You know, there are electrical engineers and there are mathematicians involved in the process, and it's usually sometimes you can find individuals which cover more than one of these disciplines, but often not. And we do have different individuals who provide the competence in each area and collaborate with each other. That is very, I think, very important. But on the other hand, it is important for a single individual, at least to a certain degree, be conversant in those disciplines. I mean, you cannot be totally ignorant of it and rely on somebody else. That has been my philosophy. So, you know, I'm good at certain things, and I'm not so thoroughly versed in other things, but at least I have some understanding so that I can talk to people who are really very good in those other areas where I'm not very good.
Thank you so much. Same order again. Yeah.
Same order. So I'll add to that by saying, personally, I've been fortunate that we built a group that literally is in the same space. We see each other every day, and it includes me as a neuroscientist, there's a biomedical engineer, there are 2 biostatisticians, there's a clinical neuroradiologist, and there's a psychologist as our faculty, and we're all in the same space. And so we work together every day. And then we collaborate with people who are the clinical experts in, like I study aging, so I collaborate with people in the aging center. I study alcohol, I collaborate with people in the alcohol center. So we don't necessarily bring that topical expertise, but all together we're pretty good at doing cognitive neuroimaging network science. But the other thing I'll say relates to the last thing he said. You have to be able to at least hold the conversations with the people you collaborate with. And for me, not being the quantitative person, I find that seeking quantitative people like you who can explain what they do to people who are not in their field is really important. And if you want to learn how to do it, talk to GR. GR can explain really complex computer science stuff to me, and I totally get it, and I totally understand it. But I work with some other people who, they write an equation on the board, and I say, well, I don't quite understand that, can you explain it? And they write another equation on the board. And I'm like, well, that didn't help me, I want you to explain it. And they're like, no, I just did explain it. And I'm like, okay, and so someone who can really cross that bridge is really important, I think. So of those of you, if you can talk to the biologists, that's success, that'll get you success.
I think it's great. I don't have too much to add. I was just thinking as we were talking through it, there's a couple of years ago, I was talking about this collaborative project, and somebody pointed out to me, there's that phrase, jack of all trades, master of none, and then it gets left off at the end, but better than master of one, right? So it's like a little bit better to be a little bit more of a generalist, I think, in some ways, than just having your sort of niche area. I think that's a liability in a lot of ways. So most people that I know who've had good success have one area that they have, they have a lot of expertise in, and they're conversant in a few other areas. And I think if you can do that, you're in pretty good shape. The 2 things I'll just offer for whatever it's worth that I do with trainees a lot, because I just feel like it really helps, at least clinically, because you have to be able to translate some of these things, and they're difficult, is either giving you sort of elevator pitch for something, so like try to explain this complicated concept in 30 seconds, and try to use as little words as you can, and then you iterate on that, because that takes a lot of practice. But the better you can get at that, the more likely your grandmother can understand it. You know what I mean? Like that kind of thing. And I do a lot of drawing DAGs, directed acyclic graphs. Like, how does this all sort of work together? They explain it to me kind of graphically, but simply. So those are just things I think that are good. They're almost just like practices to try to get into. It'll help refine your thinking and help you to communicate with other people too.
So first thing, let me say that I'm very fortunate to have my primary appointment with radiology. So at radiology we have like 2 groups of people, so the clinical faculty and also the PhD faculty. So among the PhD faculty, we have people from different backgrounds, so computer scientists, people who do biostats. We have like neuroscientists. So the composition is multiple disciplinary. So by default. So I think it's really important. So like we talk about like the super resolution algorithm, like or image translation. So for people doing those kind of work, I would challenge you to send an image to a neuroradiologist to check the images. Like they will tell you like, hey, there is a missing lesion in your image. So that's a big problem. So if they were to use the image for the diagnosis, right? So they really, because based on the images they see every day, for how many days throughout the year, they can tell very small differences. So, yeah.
Yeah, so I guess I'm closest to like students being in your shoes only a few years ago, so I guess I can tell you kind of how I did it, maybe not like in a directed way, but just how it kind of happened. So my undergrad was in applied math. I then worked in industry a couple of years doing like data science stuff, then went and got a PhD in statistics, and then did my postdoc with basically like an engineering group. So kind of like got some tastes of different disciplines. And you kind of carry that stuff with you as you go. I mean, kind of each one shapes you and your perspective, and you kind of learn different people's approaches to kind of looking at the same problems, the different types of language they use, but all the kind of, all effectively doing similar types of things. So I thought like, exposing myself to different fields, reading their papers, listening to their talks, and yeah, building that kind of translation mechanism was helpful. I guess to reiterate, even as a graduate student, kind of making friends. I had a student that I was friends with in my PhD in the physics department, who he was MD PhD, so he did physics, but he knew like the MRI physics type of stuff, and he was super helpful for a few years and like bringing me up to speed and trying to like understand where the signals I was looking at were even coming from and all of that, and it's not an easy process. And yeah, I guess the last thing I did is like, kind of bringing these things together. It wasn't like a linear thing. It was more just like, I have no idea what's going on, and then kind of like you kind of figure it out at a certain point. And so don't get like discouraged or frustrated. Yeah, my advice.
Yeah, those are great answers. Thank you so much. So we have another question actually about long-term.
Can I interrupt you for a second?
Oh, sure. Yes.
You're advancing your slides, but they're not advancing on my screen.
Sorry, there's a what?
Oh, the slides aren't advancing
It
for
looks
me.
like you're advancing the slides so that the next question comes up on your screen. I can partially see your screen, but nothing is changing on my screen.
Okay, let's try again. Did you see the certain question?
I'm seeing the presenter view. Maybe if you switch to the other.
Okay,
view,
let me just see. Oops. Sorry, can you fix this?
And if you cannot fix it, let's continue. I
think you can reload it. Reshare.
Reshare, yeah.
Yeah,
Reshare.
stop share.
Reshare?
Double sharing and then resharing again. I think there's some connection problem. Just stop sharing.
Stopped.
And then reshare.
Maybe here. This.
Well, you could point the camera at the screen.
Just share the PowerPoint. Yeah, I could.
It's okay, no matter. Let's continue. I'll try to listen to the question.
Yes, I'll make sure I speak the question very clearly. It's about long-term career planning. When you were at the beginning of your career, did you have a long-term plan for where you wanted to go in the field? And how has your career trajectory evolved, and what advice would you give to those of us trying to figure out long-term goals? That's the third question.
Okay. You want me to go first again?
Sure, yeah. We're gonna follow the same order.
All right. Well, I have to confess, I did not have a super great long-term plan. But I did, of course, have to make a lot of decisions along the way, and I think that those decisions were critical to the development of my career. And for example, when I finished my PhD, I went to Bell Laboratories, and initially I went to Bell Laboratories, or I wanted to go to Bell Laboratories, for doing something else, and they told me, okay, well, they're not interested in that kind of project anymore. They're not working on that. It has something to do with X-ray basic spectroscopy or methylines, but very far away from what I'm doing today. But they told me about what they were trying to do, which was trying to develop NMR spectroscopy at that time for studying in vivo processes, and that was not on my career plan. But I thought, wow, it's a unique thing. Nobody is doing it. It is potentially something that can grow. So I was willing to take a risk and join that group. In fact, that particular effort, in which I was initially participating in doing spectroscopy, I do Eli and has led to my victory. In some ways, I did not have a long plan. I know the fact that I like work. I was open to new ideas, and I was doing something new that looked like it was going to be potentially very useful, and that turned out to be the case. The only advice maybe I can also give from my experience is I try to work with very good people, and I think that has made a difference. I mean, the Bell Lab group was a small group, and was an excellent group, very well. And so I was surrounded with excellent colleagues, and that has also helped me a lot in my career.
Yeah. Thank you.
So I did have a long-term plan to go to graduate school and study cortical function, probably not human primates. But I got my PhD doing electrophysiology in Aplysia braziliana C-SPAN. So I was going to do that, and then I decided I wanted to do something else, so I went to medical school. So my plan changed, and I was going to be a physician scientist, probably a neurosurgeon, until I did neurosurgery, and my plan changed, and I was going to do radiology. So I had a plan to be a neuroimaging radiologist, and I went to Wake Forest and quit residency after 3 months because I didn't want to do it, and I did a research fellowship. So no, I didn't have a long-term. I had a lot of long-term plans, and none of them worked, and they're still not working. But I have a good job, and I think I'm doing good stuff, and I like it. So I think being flexible is sort of my point.
So, I was going to say, I think I don't have too much to add to that. I was just thinking. So, when I see people clinically a lot, I think one of the key things I usually tell people, just being a psychologist, is sort of like, I think about there sort of being two pieces. One is you almost have to be flexible because there's so many things that are going to change and that you can't anticipate. Being rigidly attached to any kind of like future, very, very specific career thing is almost a recipe for being kind of let down. Knowing what you're interested in at some more kind of like visceral level, kind of like, what is it about this field that you think is cool? What do you like about it? Like the more you can actually hone in on that and realize that there's multiple different permutations of that'll be a fulfilling career, I think is very worthwhile. And sometimes it gets lost in the technicalities of everything else that we're doing, but like what lights you up about what you're doing at some more basic level, you know what I mean? And trying to distill that as much as you can. And then when you're early on, I think there's a lot of times where you're working hard in sort of with sometimes a lack of clarity of exactly where things are going, but just being curious and paying attention and seeking out good people to work with, I think are all key. Whether those are sort of mentors or colleagues, but keep learning and keep sort of building yourself up. Most people who actually make spectacular changes in any field, there's usually some period of kind of having this winding path before something actually hits later on, and then all the experience that have accumulated actually is really useful for that. So don't get attached too early, but do pay attention and look for good people. Look for, try to keep learning and stay curious and know what your motivations are.
I didn't have a long-term plan, but I do think that to be genuinely interested in what you do is very important, and do what you do really well. And once you have achieved that, you can expand. So not only the problem one you have been solving, where you can solve their problems. And do talk to people because sometimes I think as students it's very easy to just focus on the method, right? But the problem you're solving might not be important, right? So solving it 100% might not get you anywhere. So therefore I think it's very important to at least get a good mentor. As a mentor, I don't do all the detailed work. My postdocs, my students, they are better than me in terms of implementation. Okay, but my role is to look at the direction, right? So this area, I think there is potential, like in 10 years' time, right? So even if you're using a very simple solution, simple method to solve that problem, that's still valuable, right? So you are moving the field from 0 to 60%. It's better than trying different models and moving from 95 to 96. That does not give you much value. So I think it's really important to know what you're doing and do it really well, but don't be stuck in the local minima. Right? Talk to someone, attend conferences, talk to those leaders in the field, and then you will get the chance at solving more important problems.
Yeah, I guess, in terms of plan, I had, a nebulous kind of idea that I wanted to research, and I liked math, and that kind of led me here, so nothing more specific than that, really. But I guess I would just reiterate that I think looking at the importance of getting lucky, basically, and finding good senior mentors, at least one that, you can trust, that you can talk to, that's helpful. I got lucky with having multiple, but they are going to know a lot more. They've been through kind of the different career stages that you have, and maybe it seemed like it would be very difficult to kind of project that before you got in there, but having someone that's been through that and kind of guide you along and identifying that person, again, yeah, was lucky with that, and so I think that was super helpful, and you can kind of identify that.
All right. Well, thank you so much. Myself have learned a lot from the discussions. Work with good people, stay hungry, work on important problems, right? Those should be the goals instead of have some other long-term goals. In terms of interest of the time, I'm gonna skip my another question and then just conclude this session. I want to say thank you so much, Camille, for making an effort to join us, and also thank you all the panelists and for the great discussions. Then I will stop this session, and then we're gonna have our dinner for now. Thank you. So